Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. We are in week 2 and this is our second lecture. Now if you recall, in our previous lecture, we had a brief revise of what we did in our first week. And the last two main important points that we discussed is the idealized curve, stress strain curve for concrete. And you can recall that you have the design curve here, as you can see. Here you have the design curve. And the main point to be noted here is the amount of strain, that is 0.2% corresponding to the yield point. And then at the time of failure, we have a strain of 0.35%. Now that is for concrete. Then for steel, again, we develop the design curve. And the point to be noted here is the strain level, as you can see here. So this is the strain level, and the design stress is what we have here, right? And the shape of the curve also, you see, we have yielding at this point, and then beyond that, because the curve is idealized, it is flat. Now with that background, let us directly move over to limit state design. Now we have a beam section, right? And the beam section having a width of say B. And then we assume that the top fiber is in compression and the bottom fiber is in tension, and that's the reason we have these steels here, as you can see. And then the distance from the top fiber, which is under maximum compression, to the center line of this reinforcement is the effective depth, that is shown by small d. It is not the total depth. Total depth is capital D, then minus clear cover, minus radius of the rebars, and that is your effective depth. Now for this cross section, we have the strain diagram shown here. Because we assume that the top fiber is in compression, so we have the maximum amount of strain in compression, and there are two possibilities. Obviously, when we have this is the amount of strain, which is here marked here, that is the level of steel, and at this point we have the strain in steel shown here. Now we can extend this line and we can also find out the strain at the extreme fiber, but because we do not consider the concrete here in the clear cover, so that's why we will mostly focus on these strain value on rebars, right? Now we have this triangular diagram that defines a location where we have zero strain at the middle, somewhere in between. And that is what is called neutral axis. Now, the point is, if the strain in the extreme compression fiber is the maximum value of strain allowed for concrete, and at the same time we have this is the level of strain in steel, then we have a limit state, which is the limiting condition. We call it balance section or critical section. In limit state design, we mark it XU, comma, limit. XU is the depth of the neutral axis from the compression fiber. If it is the limiting case, then, or the critical case, we call it XU lim. Now it may so happen that we have the strain in concrete is what is here, and then steel, it can take more tension. So we have a strain value of somewhere here. Then if we join these two extreme points, obviously we'll have a zero strain somewhere here. Now for that, we have again this X of U, but this is not the limiting case. And you all know from our discussion on working stress method, this is corresponding to under reinforced design, right? We will see that in a minute, how we can find out the sectional capacity. So the main issue here in the strain diagram to be noted, the amount of strain in the concrete. Then at the time of failure, the strain in the steel is 0.002 plus 0.87 Fy by Es. This we have already discussed in the previous lecture. Then the condition is that we have to have, this is the minimum value. We can have strain more than that because steel has ductility property. So we can actually apply more strain, but at least we should have this value of strain, and then that will give us a limiting condition for what we define the location of the neutral axis as xu comma lim. Okay. Now let us see in more details how we can find out the location of this neutral axis. So we have this strain diagram. Now for limiting case, we have the maximum strain in concrete and then maximum strain in steel. And then from the triangle, what we can write, OA is here, OA divided by AB is here. So OA divided by AB is equal to OC, which is here, divided by CD here. So if we do that, then what we get is on the left hand side we have OA, which is XU limit. So this is OA divided by the value of strain at the extreme fiber, which is 0.0035. OC, on the other hand, is the difference between this effective depth small d and OA or otherwise XU limit, and that is what is here. Divided by CD, CD is the amount of strain in the steel reinforcement, and we have it here in the denominator. So what we get effectively from this relation is that our only unknown is XU limit, that we can easily find out because we already set this D and also the grade of steel and the Young's modulus of steel, right? So if we further see the expression of XU limit, which is shown here for different grade of steels, you can see it is a factor times the depth of effective depth of the section. So for Fe250 steel it is 0.53D, Fe415 steel it is 0.48D, and Fe500 steel it is 0.46D. So as we increase the strength of steel, this factor reduces, which is obvious because if we have less value of strength in steel, obviously we need a larger section and a deeper XU limit, right? Okay, now let us move forward. So we have seen how this strain is distributed over the section for a limiting case. Now let us see what happens when we have a neutral axis which is less than XU limit. So if we have a case XU less than XU limit, then let us see what we get. Again, let us first focus on the compression side. So we have the extreme fiber of concrete, which is shown here, B prime, C prime is 0.0035, and then we have also the point of yielding, which is 0.002. If you recall, these are the two main strain values we always mentioned when we talked about stress versus strain, which is shown here. So earlier what we had stress versus strain, something like this, and this value is 0.002 and this value is 0.0035. Now this is stress versus strain. What we do, we plot strain with distance starting from the neutral axis where the strain is 0. Then strain is linearly varying over this range. At the same time, over the same distance, we plot stress which is initially parabolic, and beyond the point of this 0.2% strain, it is flat because we have already idealized the curve here. So that's how these two plots are developed over the cross section of the beam. Now, if you look at the strain profile, because it is linear, we can easily figure it out. But in case of stress profile, initially we have a parabolic part followed by a straight line. Now, let this complete section over this stress profile or stress block, we call it, have two parts, A1 and A2. We'll see in a minute what is the expression of XU, but let us just identify the distance of this point, which is at a distance y1 from the top fiber, and this A2, which is at y2. Okay. Now from strain diagram, again let us do the similar exercise. So what we have, O prime A prime, which is here, divided by A prime D prime, which is here, is equal to O prime B prime, which is here, divided by B prime C prime. Right. Then what we can figure out, O prime A prime divided by 002, which is here, is equal to XU by 0.0035. So what we get is O prime A prime, that is here, is equal to 4 by 7 XU. Now from that, what we can find out is A prime B prime, which is here, that is y1. So A prime B prime is nothing but this full length O prime B prime minus O prime A prime. So if you do that calculation, what we get is XU minus 4 by 7 XU. So it is 3 by 7 XU, and that is the value of y1. So you get the first dimension, and then we can find out the area of the stress block, because once we know y1, we know this part as well, and then we can easily find out the area A2, area A1. So area of the stress block is area of OAD O. So this part, that is A2, plus area of A, B, C, D, A. That is the rectangular part, which is A1. Now for this parabolic part, so we have 2/3 times 4 by 7 XU, which is O prime A prime. We have already evaluated that, times 0.45 FCK. So we have already discussed the value of stress of concrete. So that is 0.45 FCK, if you recall, plus 3/7 XU times 0.45 XCK. So the area of the stress block, it is very important. So we get it 0.36 times FCK times XU. So there are a couple of things to be noted here. We now define this XU, and then in terms of XU, we have identified what is the area of the stress block. Next, what we can do, we can actually find out the position of the neutral axis. In this estimation, we are yet to find out XU, because everything is in terms of XU. That we'll do in a minute. So what we do for this XU, let us see. So the position of CG from the top fiber, here you can see this is the compressive force, and it will act at the CG of this stress block. Now we can easily find out this CG because we have already evaluated A1, A2, and we already know Y1, and we know the location of CG of this parabolic part, so we can easily find out what is. Now let us complete that exercise. So the position of the CG from the top fiber is A1 Y1 plus A2 Y2 divided by A1 plus A2. So that all of us we are familiar with. And individually we know what is A1. We have already found out this is A1. We have also found out this is Y1. And then we have the summation of A1, A2, that is the area of the stress block. We have just figured it out. Similarly, for the second part also, we have the expression. Ultimately, what we get, position of the CG from the top fiber is 0.42 times XU. So this is important. So here you can see it is 0.42 times XU. So this is where the total compressive force acts over the stress block, which is marked here as C. Okay. So that you can see here. Now what we have, total area of the stress block, we have also the location of this compressive force in the stress block, that also we have figured out. Okay. Now, let us see if we move further. Now, what we have over this entire cross section, as you can see, we have C, that is the compressive force acting here, and we have the tensile force acting here. Now, they should maintain equilibrium. That is the first condition. For that, what we do, we equate C equal to T, and if we do that, we already have figured out the area of the stress block, that is here. As you can see, over this effective length of B, that is the width of the cross section, we have this stress block here. So we have figured out this cross-sectional area, and if we multiply that with B, we get the total compressive force acting over with B. That will be equated by the tensile force over the steel, and for that we know the stress, that is 0.87 Fy, and multiply that with area of the steel, and we get basically the equilibrium condition between compressive force and tensile force. Now, from this expression, what we get is the value of XU. So, if it is not a limiting section, now you have the location of XU from the top fiber, which is 0.87 Fy times AST divided by 0.36 FCK. What you can see is, for this relation, if it is under reinforced section, XU is actually proportional to the amount of steel that you provide. Now, if you increase the amount of steel, what will happen? XU will also increase, and time will come when it will actually fall over the limiting value, right? That we'll see as we'll solve some example. But for the time being, what we have is the location of XU, which is extremely important. So first we have figured out what is the limiting value of XU. Now we can find out the location of XU for a given amount of steel. Because just by looking at this XU value, we can compare it with the limiting value, and we can conclude whether we have a under reinforced section or over reinforced section. Now, under reinforced section is preferable. The reason is steel is taking the maximum amount of tension, and because it is ductile, before failure, it gives a region where plastic deformation will occur, and that actually helps the user of a structure to leave the structure before the structure collapses. On the other hand, if you have a over-reinforced section where the concrete fails, there you may have a brittle failure, and that fails all of a sudden, and the users will not get any time to leave the structure. We will see that as we progress in this design. Now, there are, as I have already discussed, two types of section. First, we started with balance section, and then we have a under reinforced section. Now, for the balance section, again, let me repeat, we start initially applying some stress. So we start from here. As we increase the stress, ultimately it reaches for the concrete as 0.0035. And at the same time for steel, this is the amount of strain. And so these two peak strains at the extreme fibers dictates whether we have achieved a balance section or not. And in that case, XU is XU limit, and we have already evaluated the expression for XU limit. Now, in case of under reinforced section, what happens? Our extreme fiber of the concrete is experiencing a strain of 0.0035, and then the steel is having more strain, which is here, which is more than this value for limiting case, and that's the reason we have this situation, and XU is less than XU limit. So this value of XU is actually less than XU limit for obvious reason that we have already seen. Okay. Now, let us again see these are the different options you can have as you progress your strain level at a particular section. You start, say, from this initially, then as you increase the amount of stress and strain, ultimately it reaches this point at the compression fiber, which is 0.0035. And here obviously we have corresponding strain level in steel, right? So this we have already seen. Okay. Now in case of over-reinforced section, let us see what happens. In case of over-reinforced section, we have epsilon c, which is 0.0035. Then epsilon s is actually less than the limiting value of strain in steel. And because it is less than the limiting value of steel, the stress in steel is also less than the limiting value. And in that case, XU is greater than XU limit, right? So if we have, this is the XU, our XU limit will be somewhere here. Now, why this is not so economical in case of structural design? The reason is shown here. For concrete, we have gone up to the maximum level, which is fine, but for steel, we do not utilize its full property. And that's the reason it is not recommended in case of structural design. Now, I have already explained, because we still have the amount of strain in steel less than its limiting value. The steel can take some more strain, but the concrete has already reached its limit, and therefore further applying moment at the section level will cause a failure. Okay, and that's why it is a brittle failure and it is not recommended. So these are again the same strain profile for different options. So as we start for under reinforced sections, then that is what is preferable. Failure is ductile with sufficient warning. This point actually to be noted, always remember this. We will not go for a over reinforced section which offers a brittle failure. Right. Okay. So now let us see how we can find out the moment of resistance of the section. Now again, for moment of resistance of the section, what we have to do? By now we know the location of the neutral axis, be it under reinforced, over reinforced, or balanced section, right? How did we do that? We equate C with T. Now for the moment of resistance of the section, what we have to do? We have to find out the lever arm. The same thing we did in case of working stress method. That time it was JD, if you recall. But here we have a different formulation. So we can find out the lever arm because we know the location. First thing, we have found out the location of this concrete force. So once we know the location of this compressive force, we already know the location of steel where this tensile force acts. So the difference between these two, the distance between these two, is the lever arm. Now, this C is equal to T because we have to maintain the equilibrium at the section level. So the moment of resistance is nothing but C times the lever arm or T times the lever arm, depending upon the way you formulate the problem. Now for a balanced section, you can do either way. So C times LA, as you can see here, is the amount of moment of resistance. So what we have here is 0.36 FCK times XU limit times B, and then times this bracketed term is the lever arm. How do we get it? We know the effective depth, we know XU. So the difference, we already know the location of this, that is 0.42 XU limit. The difference between that two is basically the lever arm. Now, if we simplify this expression, we have again for different grades of steels, we can actually figure out the moment of resistance. And as you can see here, 0.148 FCK BD square. Recall, in case of working stress method, this MR was what? R times BD square, right? We have developed a similar expression here in case of limit state method. Now for different grades of steel, we have this value varying. So first it is 0.148 for Fe250 steel, then 0.138 for Fe415, and then for Fe500 we have 0.133. As I told you earlier, we normally do not use this mild steel. We will prefer 415 and above steels here. So that is the amount of moment of resistance we get from this section, which is a balanced section. Now for balanced section, again, we can do the same thing using T times LA. So the tensile force is nothing but the allowable stress, maximum allowable stress in steel, that is 0.87 Fy, times the amount of steel you have, AST limit, then times the lever arm, which I have already explained. Okay, now again you can find out in this expression, we are yet to know what is the limiting value of steel. That we can figure out just by balancing C and T, and we get the expression of AST limit, that is the amount of steel required for balance section is here, which is 0.414 FCK by Fy times XU limit times B. So for a given section, the moment we select this concrete and steel, we can easily find out for balance section XU limit, and then we can find out the amount of steel for that balance section. In case of under reinforced section, what we have here is, again, we can go for C times LA. Then we have already explained this. The only difference is we have XU in place of XU limit, right? And similarly, again, you can find out the moment of resistance based on steel, and then obviously the same thing you can also repeat for over reinforced section. Now for the design problem, we can actually view the problem in different ways. We can see a problem where we need to find out the position of the neutral axis, then moment of resistance of the section, then AST required for the section. So if you do that, we complete the design. So we can start with section size known. Then with that known section size, we evaluate amount of steel required. On the other hand, we can have a situation where we define section size and AST both for that particular design case. So these are the different options we can have. Nevertheless, in every design, first we have to check whether we are going for a balance section. If not, obviously we'll always prefer a under reinforced section. We'll not design a section based on over reinforced theory. But we can start with cross sections and then check the adequacy, or we can find out the cross section and amount of steel. So let us take an example. In this problem, we have beam cross section where B is equal to 300 and effective depth directly given. Normally, in actual problem, we start with capital D, and as I have already explained, from this capital D we figure out what is small d. But for our example, we are given directly this small d. We also have here the amount of steel is given. We have 4 25 bars here, and we have M20 concrete, and for the timing let us consider Fe 250. Although in reality these days we normally do not prefer this steel, but for this problem let us consider. How to find out the location of the neutral axis? We again equate C with T, and if you recall, this is the expression 0.36 FCK times XU times B is equal to 0.87 Fy times AST, and from there we know everything. See, we already know AST, and then from that value we can find out XU for this case. Now recall, for 250 steel we have already evaluated XU limit, which is 0.53D. So XU limit for this case is 265. Now our limiting case has a XU limit 265, but in our case the amount of steel tells us that the location of the neutral axis is 191.71, which is less than the XU limit, and therefore this section is under reinforced section. Okay. Now let us take a different example. In this problem, what again we do? We start with the geometry of the section and the material property. So we have M25 concrete and Fe415 steel. The size of the beam is 400 by 700. Again, normally we go up to this point, that is the total depth, from where you have to figure out the effective depth. And I have already explained in the previous lecture that there is a clear guidelines for this clear cover. Depending upon the situation, depending upon the type of exposure you have, and the grade of concrete, we have specific values of clear cover that you have to maintain. We can do that, but for the time being, our D effective is given, which is 700. Now, we'll try different options. We'll calculate the moment of resistance. First, we will try with AST equal to 325 bars. Then second case, we'll go for 825 bars. And then third case, we'll go for balance section, right? So let us see one by one. So the first case, AST is equal to 325 bars. So the position of the neutral axis, again we figure out using the same equation, C equal to T. And what we get is XU in this case, based on the given information, is 147.65 millimeter. Now for Fe415 steel, again you recall XU limit we have already obtained. XU limit is in this case 336 millimeter. So what we get, XU is less than XU limit, and therefore it is a under-reinforced section. And for under-reinforced section, the moment we evaluate the moment of resistance, we consider compression times the lever arm, as we have done here. So the compressive force C, we have figured out this is the value of compressive force. I have already explained that earlier, and this is the value of lever arm. So when you put these two together, you will get the value of moment of resistance for this cross section, which is 339.19 kilonewton meter. Now, we have tried that moment of resistance from the tensile force also. You can see here we have this is the value of tensile force times the lever arm is here. And ultimately again we get the same value of moment of resistance, which is 339.1. For the second case, we have a different value of steel. First again what we do, we find out the location of the neutral axis by balancing C with T. Again we use the same expression, but in this case we have XU, which is 393.84 millimeter. And obviously this is more than the limiting value, which is 336. Therefore, this section with this amount of steel is now over reinforced section. Okay. Now, for this section, the exact position of neutral axis will lie between XU limit, that is here, and this 394, because the stress in tension steel will be less than, because this is a over reinforced section. The stress in steel will not fully develop, right? Now, from that point, you can actually find out the moment of resistance, which I leave it as an exercise for you. The third case, where we have the balance section. So first what we do, we find out AST limit. We have already discussed this expression, AST limit. And for that balance section, the amount of steel we straight away figure out from this given material properties, and what we get is 3351.90 millimeter square is the AST required for the balance section. So if I summarize the entire discussion that we have for singly reinforced section design as per limit state method, these are the following steps that we follow. First, we calculate design or factored or ultimate bending moment. How do we get it? We first find out the working bending moment or service bending moment, and then we apply appropriate factor of safety. Recall, we have different load combinations, dead load plus live load and so on. So we do all these load combinations and then first find out what is the critical value of load that we apply. Because we are talking about now the design against flexure, so we find out what is the design value of bending moment. That is the first step. Then what we do? We calculate limiting value for a given section. So what we do, we assume a section because now we have to design. So we start with a section with some proposals of steel and concrete. For that, we can find out mu limit, which is Q BD square. Recall in case of working stress, it was R BD square, a similar expression. And for different values of steel Fy, we have different values of Q here, as you can see. Then the third step is we have to check whether applied bending moment is less than mu limit. Then we can design the under reinforced section accordingly. If the applied bending moment is more than the mu limit, then obviously as per singly reinforced beam theory, it will fail. So we can go for doubly reinforced. This we will discuss as we progress in this course. What we do, instead of having steel in the tension zone alone, we can have steel in the compression zone. Now, coming back to this under reinforced design. So again, what we do, we use the expression for under reinforced section, and first we find out what is XU. Then we find out what is the appropriate value of AST for that particular section. There is an alternate approach, as you can see here. What we can do, in this expression, we know the left hand side. On the right hand side, you see this is a quadratic equation of XU, and that we can solve and find out what is the value of XU for this applied bending moment. And then once we do that, we can then go back to this expression and solve the problem completely. So this is another way to solve the problem. And then finally what we do, we find out the amount of steel required. Now, finally, once you find out the amount of steel required, there is a guideline in IS 456. That guideline says you have to provide a minimum steel of 4%, and you also have to satisfy this criteria as per the clause 26.5.1.1. What it says, AST minimum divided by BD should be greater than this value, and that you have to maintain just to prevent any sudden failure and for ductility. That I have already explained. Now, this minimum amount of steel we have to provide, which is required for this section when we apply the bending moment U over this cross section. But we cannot go for beyond this 4% of the gross area of steel, because once you cast a formwork and then you first place the steel, then if it is more than 4%, then it is very difficult to pour concrete here and go for proper compaction. If we do not have proper compaction, then there will be honeycomb, and that will lead to lower value of strength of concrete, which is not desirable, and that's the reason the maximum amount of steel that you can provide is 4%. So with this limit, if you design, it will satisfy all the code clauses, and you can get a section which will offer sufficient strength against your applied bending moment. With that, let us close here. You go through all these derivations. As we continue in this case, we will solve some more problem. If you have any query, do let us know. We will solve, or otherwise in the open session also you can discuss. Thank you very much.